Can we imagine a way to play with the electrical activity of the brain without any surgery or any implants? This is what's called non-invasive neural stimulation, and it was the subject of my conversation with Professor Eric Głowacki. Eric has a background in materials chemistry and a passion for electrophysiology, a very interesting combination that not only produced a fantastic research output, but also made this conversation all the more fun. I hope you'll enjoy it. Hello, Eric. How are you?
Matteo, I'm great. It's great to see you and to host you here.
Thank you. It's my first time in Brno.
Yeah.
Man, it's beautiful, has charm, it's vibe, it's full of students.
Yes.
How do you enjoy your life here?
I enjoy my life here a lot, and a lot of the things you said are the reason. There are a lot of students. So there are 3 big universities, there are 2 large university hospitals, a lot of research centers, so a lot of companies, technology around. So it's a vibrant city from that creative point of view. People are doing interesting stuff. And yeah, it has a cool vibe and culture, and it's not Prague, right? So the thing about Prague is it's beautiful, but Prague is very much a tourist destination. So it's very much full of tourists, a little bit suffering from over tourism. And that's a problem that Brno does not have. It's really not on the radar of tourists. It's a really good city for visiting, of course, but really for living, I think it's fantastic.
I read that you have a passion for rescue, emergency rescue, and first aid.
Yeah.
How do you cultivate that hobby?
Well, I have not been cultivating that hobby in a very, very long time. That's something that I did as a high school student, and then later as a university student. So during high school, I took paramedicine courses and got trained then in a volunteer first aid and rescue squad. And I did that for about four years, and it was very formative. I really learned a lot, not just about some practical, basic medical issues, which of course definitely influenced something about how my future went, but it's a kind of character developing thing. I mean, you learn how to deal with stressful situations, you learn how to deal with people in very specific psychological circumstances. I mean, usually when people are calling, emergency number and the ambulance is coming, this is very likely the most stressful thing that ever happened to them in their life. So you're basically constantly dealing with people who are in a very heightened state of psychological arousal, and that's just an interesting thing to experience, especially as a very young person. And I just feel that was very formative, and it's something I definitely recommend to, if people are interested, to get involved, because a lot of volunteer first aid and rescue squads, they need people, and it's something I think could be really, really great thing to do.
There's a lot I would like to discuss with you today on the scientific side.
Exciting.
And I would like to start from a moment in your life and career that must have been important to you. That is in 2016,
Yeah.
when you win a prestigious award in Sweden that allows you to move from Austria to Sweden.
Yeah.
And start your own research group and start looking at questions that then became your bread and butter. Tell me what that moment meant for you personally and professionally.
Well, that moment was indeed very pivotal for me, and something that was a great honor that I did not exactly expect. It was a kind of constellation of the right circumstances and the right people. But in short, yes, I received something called the Wallenberg Molecular Medicine Fellowship, which at that time was recruiting young faculty, basically a couple years after PhD, into a couple of different universities in Sweden to explore different topics in molecular medicine. And in fact, what I was interested in working on and what I was recruited to do was rather different than most of the molecular medicine stuff that was going on. And I was really interested in looking at molecular organic materials and their capacity to create these crystals that are stable in aqueous physiologically relevant media, and to charge up and basically either create electric fields in that solution in a reliable way, and or actually run electrochemical reactions. And I was very interested in reactive oxygen species, in the reduction of oxygen to hydrogen peroxide. And this is the topic that I worked on in parallel with essentially using these types of organic molecular materials for direct stimulation of cells and tissues with light. So the idea was to transduce light impulses into electric fields that would then stimulate a target tissue. So those were the topics there. It was all about light and organic crystalline materials. That was the essence of it at the time.
I would like to continue on the stimulation part, in particular, non-invasive neural stimulation. It comes in many shapes and forms.
Yep.
And I would like to discuss a few of those with you. Starting with temporal interference. It's a topic that you spent quite some time and energy on, and just tell me the basics of TI and how does it work.
Yeah, so the basics of temporal interference stimulation is that it is a type of non-invasive electrical stimulation. And to understand why people are excited about temporal interference, we have to look at some of the fundamental limitations of non-invasive stimulation. So non-invasive electrical stimulation means that we have electrodes which are placed essentially outside of the body. They're placed on the skin. Either they are on the skin above the skull in order to stimulate the brain directly, or somewhere on your body to stimulate targets like peripheral nerves. And of course, this has a huge advantage that it's very easy to do. There's no surgical procedure involved. It's safe. It's well established. So of course, the adoption of electrical stimulation is quite facile for both research and for clinic. But the fundamental problem is that you simply cannot stimulate structures which are very deep below the skin. You can essentially only target things that are quite superficial, maybe down to a few millimeters below the skin. Because you have simply the basic physics of the fact that electric field will get smaller with distance from the electrode. And you can, of course, just pump up the voltage, pump up the current that's injected into the subject, but you cannot do that forever because you're going to overstimulate a lot of sensory structures in the skin and also sensory nerve fibers, and it's going to start to become increasingly unpleasant for that person. So there is a practical current limit that you can apply, a kind of threshold limit, to where you simply cannot apply more current to target a deeper structure because it's just impractically unpleasant for the patient and also potentially damaging. So the thing about temporal interference that really captures people's imagination is that it purports to go around and somehow solve this very, very fundamental problem of targeting deep structures. That the notion is that if one can use multiple currents, which then interact in a geometrically specific way at a target structure deep below the skull or the skin in the periphery, that one can somehow circumvent this fundamental limitation. And that's, of course, a very, very exciting idea. A lot of people have thought about this idea, how to, overcome this basic limitation of the distance relationship of electric field. So the way that temporal interference works is that one is applying two or more so-called carrier waves, carrier frequencies. So these carrier frequencies are electrical signals that are in the frequency range of 1 kilohertz and above. So typically several kilohertz, sometimes even tens of kilohertz. And these are frequencies which are correctly regarded to be outside of the window of physiological neuron activity. That basically, when you look at neuronal oscillations, of course, we're talking about frequencies that are relatively low, so typically below 100 hertz. And then, action potential essentially in the frequency domain is 1 kilohertz, right? It's 1 millisecond, 1 kilohertz. So the idea is that, well, you can use these very high frequencies that are above this physiological range, and you can use, for example, one frequency which is, let's say, 4,000 hertz or 4 kilohertz, and then another one which is 4,010 hertz. So you have two frequencies. There's a difference between them of 10 hertz. And if we now apply both of these frequencies, for example, to the scalp, so we have two electrodes here, these currents will be injected transcranially, again, 4 kilohertz and 4.01 kilohertz. And what's going to happen is that these electric fields will interact, and they will constructively and destructively interfere. And they will constructively and destructively interfere at a frequency which is equal to that offset frequency of 10 hertz. So you end up getting what's called a 10 hertz amplitude modulated envelope. Essentially, the electric field amplitude is going up and then down, up and then down, and it's oscillating up and down sinusoidally at a low frequency of 10 hertz, right? So we use these high frequencies to produce this 10 hertz envelope inside. And one of the basic assumptions that many people make is that one is going to get selective 10 hertz actuation of a given neural target, and that the superficial structures which are being exposed to this unmodulated 4 kilohertz or 4.01 kilohertz signals are not going to be stimulated, or not going to be stimulated in any kind of meaningful way. So essentially, it's a way to deliver a 10 hertz stimulation at some target site deep.
Okay, this is already a bit surprising to me. Maybe I'm wrong, but typically when you have two waves with two frequencies that interfere, then you create, this new wave that has a particular shape. But if you decompose it, you still have only the two original frequencies.
That's correct.
While in this case, it seems that there is an effect at a third frequency.
Yeah.
Where is that third frequency coming from?
That's a very good question, and that's been a topic of our research and quite some debate in the community. Because at face value, if you just look at it from a textbook electrical engineering perspective, you're absolutely right that this the total power as a function of frequency is essentially only high frequency. We're gonna see these power bands at centered around 4,000 and 4,010 hertz, and in the low frequencies, there's not going to be any power. In order for there to be effective power at the low frequency, in the low frequency region, we have to have a phenomenon called demodulation, right? So demodulation is where one can have some kind of nonlinear electrical element, like a diode, which is going to extract this low frequency envelope. So the thing is that people observe in many cases incontrovertible evidence that at the site of interference being maximum, right, that you really do get actuation. You get essentially some kind of phasic neuronal activity, which is synchronous with this low frequency, this 10 hertz envelope, for example. So you can very quickly experimentally verify that, okay, I have 4,000 hertz, I have 4,010 hertz, but the neural activity I'm measuring has a synchronous frequency of 10 hertz, right? So that can be experimentally verified. But the question is, what is going on? What is exactly, causing that neural activity at that specific low frequency when there is in fact no power in this, as we established, there's no power at this low frequency. And that's been the topic of our research for some time now. And I mean, I can, get to the conclusion and say that essence of what's happening is that the actual depolarization of the neurons, which leads to action potentials, is being recruited by the high frequency itself, by the 4 kilohertz, so to speak. And when you have this amplitude modulation, what's happening is that the amplitude of this 4 kilohertz is actually going up and down. So what happens is when the amplitude is very low, we don't see any neural activity. Not surprising, right? When the amplitude goes up, the neural activity we're looking at turns on. So what we've been doing experimentally is trying to carefully measure using different models. Both, when I say models, I mean actually computer models, calculations, and also experimental models, where we're actually doing this in animals and also in humans, to see, okay, is there a practical difference in the threshold, so the amount of current we need to recruit neural firing between the unmodulated carrier, right, so this 4,000 hertz, or 4,000 hertz that's modulated at 10 hertz, right? And we explored different modulations and so on. We really tried to tease apart, is there a practical difference, right? Does the neuron or the neurons or the network of neurons somehow selectively, preferentially get stimulated by this modulated, low frequency modulated kilohertz signal? And the answer is that in most cases, no. There really is no practical difference in threshold. And the actual threshold depends purely on the kilohertz frequency itself, not on the low frequency. I should qualify that by saying there are cases where we do see meaningful differences, where we see dips essentially, where at certain modulation frequencies you get you can have an effectively lower threshold, but we're talking about effectively lower threshold on the order of 10, 20%. And when we talk about it from a practical perspective, if I'm trying to apply, for example, to your head these carrier frequencies and trying to stimulate something in the middle, let's say that at the target I can get at the amplitude modulated frequency I can get 20% lower threshold, but the actual amplitude of the stimulation signal is going to be dropping, right, with 1 over r, right? So you get this brutal drop over distance. And so what this effectively means is that all of that neural tissue, intervening neural tissue between the electrode and your region of interest, is going to be exposed to this unmodulated or relatively unmodulated high frequency carrier. And the question is, what's going on there? What are those neurons doing? And what they're doing is they're being exposed to what's called tonic stimulation. Tonic stimulation means like constant stimulation. And what neurons do under high frequency tonic stimulation with these high frequencies is rather interesting and not very well known to most people throughout not only the neuromodulation community, but also even like more basic electrophysiological community. It's not that widely known. But what's happening, which we have experimentally verified, is that essentially as you increase the frequency, at some point you reach threshold and the neuron starts to fire. Of course, not at that high frequency because it cannot fire action potentials at 4 kilohertz, right? It can fire action potentials at a lower frequency, and it will fire at some preferred frequency of, let's say, 5 hertz. And then as we increase the intensity of the unmodulated kilohertz, it will fire faster and faster and faster. You get this interesting amplitude frequency dependence. And at some point, what you see is that you'll get 1 or 2 action potentials recruited, and then the nerve will be stuck in refractory period. And essentially, you get what's called nerve conduction block, which is something that also there are active community of people who have been working on that for decades. And this is the result of kilohertz stimulation. And I was saying something before about how we're measuring it and we have some very nice experimental and computational evidence about how this works. But a lot of these things have been recorded in the past. And there are some papers from as early as the late 1930s and 1940s, and then several important ones in the 60s, that document the phenomena I just talked about and look at amplitude modulation and things like this and how it affects threshold. And the problem is these papers are very widely ignored. And the reason is that most of the fundamental ones, the really pivotal ones in this field, they're actually written in German, right? So the old German electrophysiology papers, which are very good papers, but they simply in the English language literature have not been cited, right? So these papers, if you look on Google Scholar, they're cited a handful of times in the past 50 years, right? So essentially, they're not very widely known. There have been communities over the years that have looked at this kilohertz stimulation and have mapped out something called strength frequency dependence, which is this phenomenon of as you go to higher and higher frequencies, you need higher and higher intensity of the kilohertz current to elicit the same effect, right? That's something that's been, let's say, documented in the literature, but again, largely forgotten about. And what we've been working on recently is basically bringing this kind of old models and old formalisms back into the spotlight, measuring these things, let's say, using slightly more modern techniques, and looking at this directly in comparison with temporal interference, and seeing that the take-home message is that temporal interference stimulation seems to be driven by the kilohertz stimulation itself. Which doesn't mean, Matteo, that I think that temporal interference is not useful. I think there's many reasons why it's useful and interesting, and there are, of course, compelling results from human non-invasive brain stimulation studies, and I think this area is very worth pursuing. But what I definitely want to set the record straight on is one cannot regard the carrier frequency as being somehow inert, or somehow, not being able to have an effect. It is a part of the story, and any kind of trying to understand what these modulated envelopes are doing cannot be done while ignoring the effect of tonic stimulation elsewhere. That tonic stimulation elsewhere may or may not be a problem for a given application, but it very likely is part of the story and should be very carefully considered.
And clinically, what is TI offering that other technologies cannot, and for which application do you imagine it used in the future?
It's definitely get to the applications, but I want to answer your question starting with some kind of, let's say, lower level looking at TI, right? So we were talking before about this phasic stimulation, where basically the waves meet, and you get this interference at the low frequency. There you have phasic recruitment. You have something happening at this 10 hertz or whatever, right? And then at areas that are around that, you get this tonic stimulation, which is more intense because of 1 over R, right? It's more intense, it's tonic. So you kind of have this, I call it core shell structure, right? So the kind of shell is being hit with this unmodulated kilohertz, and the core is being hit with this kind of modulated kilohertz. And that kind of spatio-temporal pattern is rather unique. In fact, I think that's very cool. I think the notion of selectively stimulating something in the middle of the brain, for example, is not really on the table, right? But people have shown a lot of interesting applications in peripheral nerves. We have a cuff electrode, for example, and you get this kind of core shell pattern, right? So people are looking at this for the cool thing is that you can use many different electrode pairs, and you can change the ratio of the currents between them, and you can actually change the position of where this low frequency phasic hotspot is, right? You still will have the tonic stimulation around, right? But you can play around with the position, and I think that can be potentially very cool. So at the fundamental physics level, you have this spatial temporal kind of control, which is rather unique. Now, you asked about, like, okay, really clinically, so where can this matter? And I would answer that it's relatively early days, because us and others, right, we've done different types of trials on patients and seen interesting and beneficial effects, which clearly are tied to the modulation frequency, or appear to be tied largely to the modulation frequency. So you can get interesting types of stimulation of the brain or peripheral targets and obtain some kind of therapeutical outcome. But I think a lot of the benefits are coming from not necessarily the TI itself, but the fact that this kilohertz stimulation is recruiting different types of it's a different way to recruit neural firing, right? And again, when I say neural firing, everything we've discussed up to now has been, it's at the super threshold level, right? So we're actually inducing action potentials. The timing of action potentials, the interspike intervals, this kilohertz stimulation is doing this quite differently than a lot of the established stimulation modalities. So I think that maybe some of the effects that we're seeing are tied to this. So, but I think it's relatively early to say that there's one concrete application where TI clinically is like the solution, where other, for example, non-invasive brain stimulation modalities have completely failed. I don't see that dichotomy yet. I think it's a very cool area of exploration, and our small contribution to this field has been really, you have to consider the kilohertz itself, that this is behind the mechanism of what the individual neurons are actually doing, and how we're depolarizing the membrane, either sub or super threshold.
As far as I understand, there's not perfect alignment in the community,
right,
on the mechanism of TI. Is this the core of the disagreement?
I think that this is essentially the core. It's difficult to point a finger at exactly. I would say that there is one kind of, let's say, point of contention has been this capacity of high frequency signals to stimulate meaningful neural activity at all. So a lot of TI studies that you see there out in literature, you'll see in introduction sentences like that neurons, are not stimulated by these high frequencies. They will not, fire at these high frequencies. They will not be stimulated at these high frequencies, but they respond to low frequencies, right? To which one asks, well, but there is no low frequency content here, right? But we talked about that already. So one thing is this kind of like a lot of people still seem to kind of overlook the fact that these kilohertz electric fields also depolarize neural cell membranes because of phenomenon of neural membrane rectification, which is something that we and others have published on, both computationally and experimentally. That's one point of contention. And the other point of contention is that does all this, do all these results really hold when we look at subthreshold phenomena, right? So subthreshold phenomenon, this is where, all the amplitudes that are relevant in the experiment, they're not enough to recruit neural firing directly. And this is where we get into the territory of non-invasive brain stimulation. Non-invasive brain stimulation classically has been subthreshold because the safe and comfortable limits of current that can be injected into the brain, typically around 2 milliamperes through a single electrode, simply the electric fields inside the brain are not enough to depolarize the neuron to fire, right? As a DBS electrode would do, right? DBS electrode inside the brain, this is suprathreshold stimulation, right? Electrode outside of the brain, this is subthreshold.
Is it wrong to say that what's happening suprathreshold is stimulation and what's happening subthreshold is modulation?
I mean, the modulation, so to say, is the same, right? What our models show is that the kilohertz frequency is modulated like this, right? The neuron will at a certain point, the membrane potential will ratchet up, and if you're in the suprathreshold regime, it will start firing action potentials. If you're in the subthreshold regime, you'll just see these lower frequency membrane oscillations.
How do you see that experimentally? If you excite a neuron, you see an action potential, so you have a biomarker. But if you have something subthreshold, how do you look at it experimentally?
Well, from the point of view of a single neuron, the only thing that you can do is you can look at these high frequency oscillations of the neural membrane, right? And you can low pass filter it
Which
and
you
look,
can measure.
which you can measure, and then you can see that the membrane is being net depolarized, and net depolarizes only a few millivolts,
Okay.
and then it's not enough to fire an action potential. But the subthreshold stimulation in general is relevant not at the level of single neurons, it's relevant at the level of networks and larger structures in the brain, where we have all these low frequency oscillations, right? And the classic model of subthreshold brain stimulation, whether we're talking DC or low frequency AC transcranial stimulation, is that you're slightly depolarizing and hyperpolarizing the neurons and basically increasing or decreasing the probability of a given population of neurons to fire. So what that causes is it basically causes these oscillations, the statistics of these oscillations to be modulated a little bit, right? So the kind of the textbook way of saying it is that suprathreshold stimulation, you get, for every impulse, you get a recruitment of action potentials, right? That's suprathreshold stimulation. Subthreshold stimulation is you're modulating ongoing neural activity. The neurons are talking to each other, they're doing something, there's oscillations between these structures, and by applying an external electric field, you are pushing the statistics of the neural firing in one direction or the other. And that, of course, can have very meaningful impact on the overall thing. So, it's subthreshold stimulation is very important and relevant, but we have to kind of look at it a bit differently than suprathreshold stimulation. Also, I want to mention another kind of neurobiological thing that's important to consider. When one does stimulation of purely axons, so if you have a peripheral nerve, right, it's just axons there, right? The cell body of the peripheral nerve is in my spinal cord, right? So there's no synaptic activity here. There's just a wire that's going, action potential is going there. So there is no relevant subthreshold stimulation that can happen there. You're either a super threshold where you cause an action potential, or you don't, right? And you're below threshold. That's when we talk about axons. But in the brain, right? I mean, we have this synaptic activity where you can increase or decrease the probability of neurons to end up firing because of many synaptic inputs, right? This subthreshold pushing things around with lower electric fields is of course a super interesting phenomenon. I'm not the most qualified person to comment on that, but I should say that our results have always, or our measurements have always been on axonal stimulation, where like the picture is very, very clear about this kilohertz business, right? There definitely can be some other nuanced activity going on when we have real synaptic activity.
Okay, I had never thought it that way. And I want to use this to pivot to another topic that I'd like to discuss with you, because both the modulation and stimulation are very important for retinal stimulation.
Oh yeah.
So I'd like to talk to you about retinal stimulation and retinal implants, which is a field that saw much progress in the latest years. I'm curious to know your opinion on this recent developments.
Yeah, that's a very, very interesting question. And indeed, this dichotomy between superthreshold and subthreshold is kind of a logical link in this story, because the thing about retinal stimulation, the idea has been around for a very long time. So just a little bit of kind of neurobiological background to set the stage here. As many people know, the retina in the back of your eye is actually a part of your central nervous system. And it is responsible for transducing inputs of light from our visual world into a meaningful neural signal that your visual cortex then interprets into a meaningful movie of our life, right? So there are several important structures in the retina. It's very complex, but we can kind of look at a couple of important layers. The first layer is the photoreceptor layer. These are these rods and cones, basically. These are photosensitive cells where the basic transduction of a photon into some kind of neural output is happening. These are highly specialized, sensory cells that are, in fact, they're metabolically very demanding, and for that reason, there are different diseases where these highly specialized cells are actually dying. They're degrading, and they are disappearing. And what happens is that the patients become progressively they lose their sight, and they become effectively blind. But the rest of the retinal circuitry that's in there is still intact. So the photoreceptive cells are dead, but or many of them are dead, but the rest of the neural circuitry is intact. And the rest of the neural circuitry, what I mean by that is there are these layers that directly connect up with the photoreceptor cells, which consist of these are bipolar cells, mostly bipolar cells, amacrine cells, horizontal cells. These are also sensory type structures. They're typically not spiking cells like action potential generating cells, but they are neuronal-like, and they are responsible for essentially processing or pre-processing the signal that comes from the photosensitive rods and cones. And then this layer of these bipolar cells connects up to what are called retinal ganglion cells. And retinal ganglion cells are proper neurons in the sense that they're spiking neurons. They send action potentials. And this is all exceedingly complicated because there are at least a dozen different types of cells in this sensing bipolar layer, right? And then retinal ganglion cells, there are around 25 types from last time I checked, of which only several of them are really, really well understood. And basically this whole device, it's a device. I mean, it's amazing, right? It is converting it's taking an optical signal, and it's doing a lot of analog processing. So a lot of graded analog processing. And then basically with the connection to the retinal ganglion cells, which all are very specific, basically creating an image, or movie, I should say, of the world, which is like every single retinal ganglion cell type is creating a different type of image. So there'll be different colors, right? there'll be, types of retinal ganglion cells which transduce motion, right? Or high contrast, for example. And then all of these like Photoshop filtered movies are going into the visual cortex. Visual cortex is then making sense of that, right? So people realize that, okay, if you have a disease where the photoreceptors die and the rest of the neural circuitry is intact, well, why don't we use neural technology to stimulate this the retina? It's an idea that's been around for a long time, and it's been the graveyard of companies, right? 5 or 6 companies, I think that number is plus minus correct, have gotten very far, up through clinical trials, patients, and have gone bankrupt, right? Because the result for those patients, basically the outcome in terms of impacting the quality of life of these patients with blindness, degenerative blindness, were simply not meaningful enough to make it worth it, right? What these patients were seeing were basically these blobs and flashes of monochromatic light with very, very low resolution. Essentially, they can tell that there's a bright window or light over here. Maybe there's some bright person in front of me, some figure. It's very, 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 very low quality vision that certainly, well, apparently from a commercial perspective, was simply not worth it. People didn't find it worthwhile.
From a neuroengineering perspective, what's limiting the development of the technology? Is it the neuroscience? So how to efficiently encode the signal in the retina so that the brain interprets it naturally? Or is the engineering part, so making a device with high density that can be implanted and works well? Which of the two parts would you say it's most limiting?
To some extent, both, but definitely the whole neural processing part that we're ignoring, because basically the prevailing way of thinking was that the retina is a camera, right? You have all this neural circuitry, and basically these rods and cones, these are pixels, right? These are pixels which, just like pixels in a CCD, are converting an optical signal into an electrical one. So what we have to do is we have to make a high density array of pixels, right? Which is of course a neural engineering challenge, but it's something that can be done, right? You can make a lot of electrodes. You can make a high density array if you try hard. But then what these arrays were doing was targeting essentially the excitable cells, the retinal ganglion cells, right? And thinking that, okay, well, there's these 25 cell types, but throw that out the window. We're just going to stimulate them with some kind of spatial, relatively high spatial resolution. And we're going to look at the output at the super threshold level. Why? Because as engineers, we like super threshold, right? It's like you apply a stimulation, you see an action potential, right? You can measure the current that you need to elicit this activity. You can measure the current thresholds. You can map this out. To people like myself who are trying to make photovoltaic arrays, we knew exactly how much current density we need, how much charge we need to deliver in order to achieve a certain outcome. And then we can think as engineers, okay, how are we going to make the pixel small? How can we decrease the impedance so that the voltage is enough to deliver the current, and so on? We can be engineers about that, right? But all of this wonderful engineering was for nothing, because you're just taking this complex neural circuitry and you're basically beating it with a hammer. And yeah, the brain is getting a signal, which it sees as this flash of light, but this is completely bypassing all of the normal, pre-processing, pre-amplification, and actually sampling that the retina is doing. And the key, innovation was actually not so much technological. It was also relatively high density array, but to actually go from the other side of the retina and try to stimulate those non-excitable, essentially bipolar type cells, which have this graded potential, right? You can hyperpolarize them, depolarize them at a, here again, actually using the word subthreshold is maybe not completely correct. Subthreshold in the sense that we're not trying to kick a cell above a certain potential to create an action potential. We're just adjusting the potential up or down, and doing it with some kind of spatial summation. So let's say we can get a lot of pixels in a row that are stimulating these cells in a spatial pattern. We can also temporally, we can do temporal summation. We can have a lot of pulses, and we can adjust these potentials of this analog layer of cells that then connect up to the digital RGCs, the retinal ganglion cells. And okay, this is still really oversimplifying like the real neural circuitry, but it's much more elegant solution than just taking the retinal ganglion cells and non-specifically beating them with a superthreshold signal, right? You're plugging into this analog processing, and the result, from the point of view of patients who are now in these clinical trials, is qualitatively a huge step forward, right? So we're talking about patients who now are able to actually read, who are able to navigate in the world, who are able to, for example, go into a bus stop or a subway and pick their head up and read the name of the street where they are. It's not super high acuity vision, but it's relatively impressive, and it's bringing these patients much more meaningful benefit. And the improvement was not really in the neural engineering. This device is engineering-wise, of course, very impressive. I'm not trying to, and I know the people who did this work, and it's fantastic. But there isn't some kind of like massive, oh, we made 1,000 more channels or something. No, they plugged into the natural neural processing in a smarter way and achieved a different outcome. And the exciting thing for me as a neural engineer interested in also in this photovoltaic stimulation is that the actual voltages that you need to do this type of subthreshold stimulation are pretty low. So suddenly the engineering problem actually became easier, became much easier, and that's very exciting.
And as far as you know, commercially, the topic was picked up again by companies.
Results I was now discussing, there are clinical trials that are being run in, I believe, 4 or 5 different countries by a company, a French-American company that essentially originated from intellectual property from Stanford University, from Daniel Polanker. So he, of course, does very nice work on animals, but these are clinical trials being run by a company. So there is definitely commercial interest. I don't know about other companies that are out there in this space. It's definitely rekindled my interest, because a couple of years ago, I definitely thought retinal stimulation is not something I want to work on, because I saw this relatively tragic results for these companies that were just going out of business, and because they were basically not providing a meaningful benefit for the patients, right? So I thought, okay, well, I can make as many channels as I want and make the electrodes as low impedance as I want, and it's just not going to do anything meaningful. But this different way of thinking actually, opens up the possibility to rekindle my interest, let's say. Yeah.
I think these last minutes of conversation really highlight one of your key strengths, that is the ability to combine your background in materials chemistry and materials science with an interest for electrophysiology.
Mm.
Two very different fields.
Yeah.
One much more maybe chemistry oriented, the other one biological. How much fun it was to learn the two and interact with people with a very different background. How challenging, and was it a necessity or something that you found interesting during the way?
It's a challenge, of course, but I think it's also very fun. And by doing this kind of interdisciplinary research, one can do meaningful and interesting things. But it is hard, and one really has to spend the time and have humility and patience to relearn essentially new fields from scratch. And also, it's very important to find the right partners who are open-minded and who are also very knowledgeable, and with whom you can engage into a meaningful collaboration. Why I happened to choose this path that really went, from material science to, let's say, cell level electrophysiology, and then, let's say, more neuromodulation and bigger systems and more clinical systems, is just because I found it fascinating and interesting. And by no stretch of the imagination am I a neuroscientist or a biophysicist in the sense of field. I still am at heart a physical chemist. Those are the things that I feel most qualified on. But I definitely love applied neuroscience, and I feel like I know at least something about the topic to engage with people who know much more than me, and then to do something together that actually is interesting.
I have an electrophysiology related question. Maybe you can help me answer that. If we have an electrical signal, we can go there with an electrode, stick an electrode, and measure something. If we want to do it with high density, we just put many small electrodes and try to have a high spatial density. Then, since every electrode becomes smaller, impedance goes up.
Yeah.
And it goes up especially at low frequency because of how electrodes work. Which means if we want to read with high spatial density some low frequency signal, it becomes challenging. Now, the point is, and I think this is interesting both fundamentally and technologically, I cannot think of a low frequency signal that would be interesting to measure at high spatial resolution. And my question is that because I simply cannot think of one, or because there's a relationship between how quick a signal is and how spatially localized is that? For example, a neuron fires very locally. If you look at maybe the heart, it's already a bit slower, but it's more spread out. And if you look at something much slower, such as spreading depression or maybe chemicals changing throughout the body, it's very, very slow, minute or hour period, but you don't need to go there and measure at high spatial resolution because it's very spread out. So is there a relationship between the temporal and the spatial properties of signal or not?
Yeah, so I think from the like classic textbook point of view, there is that exactly that relationship that you pointed out. When we talk about neurons, right, and we go single neuron and we zoom out to groups of neurons and then larger networks of neurons, that the low frequency content of the signal is appearing as we go to bigger populations of neurons, where we basically see these oscillations that originate from neurotransmitters actually, and then charged molecules which are being in concert, sloshing around the system, and we record this, and if we're to, and this originates from network activity. It doesn't originate from the individual neural activity. So when you said, is there a meaningful like signal to measure with low frequency content with very, very high spatial resolution? It's a tricky question. I mean, the first order in the kind of classic spatial temporal discussion, spatial frequency model that we just talked about, I guess not. But I don't know. I guess you can imagine if you're looking at a synapse, like or very close to a synapse, these are low frequency electrical signals, and I'm not aware of how people have measured that, other than, of course, there is a very vibrant field of people who try to look at synaptic electrochemistry, basically directly measure neurotransmitters, using some advanced electrochemical methods. People do it. It's challenging, very, very interesting. There are people out there like Bernhard Wolfram in Munich who are much, much more qualified to speak about this than me. But I suppose, and maybe I'm saying something on the record which is nonsense, but I do think that if you do have a very small electrode that is also of low impedance, that you could collect this kind of synaptic release of charged neurotransmitters. Maybe there's something meaningful there.
All right, we talked about non-invasive stimulation in its electrical form, optical methods. One could do it acoustically if you use ultrasound, but also chemically. You can modify the concentration of a chemical around a tissue or a cell and see how that gradient or that change influences the activity of the cell.
Mm-hmm.
And you've played around with oxygen concentration, peroxide concentration with tissues, maybe also in vivo. What's the idea there?
Yeah, that's a very fun question. This is something that's been kind of a thread of research that I've been engaged in for a long time, but in the past couple of years, it's really bumped up a lot of attention on that. The basic idea is this, that neurostimulation, whether we're talking sub or super threshold like before, right? We're talking about electric fields influencing excitable cells by basically depolarizing or hyperpolarizing cell membranes. That's neuromodulation, right? Neuromodulation is acting typically at that level of electric fields, right? But if you stick an electrode into a tissue and you have an interface between electrode and basically the biology, It's a wet environment where you also have charge transfer reactions happening. Some of that charge that you use to create that electric field for your stimulation, it goes off and gets transferred to different species, molecular species in solution. And it turns out that this process is not always reversible. In fact, I would argue, and we've published papers to that effect, that it is very much irreversible in many cases. So there is this dogma that exists of charge balanced biphasic stimulation, right? That's the way everyone does it. Essentially, you put an electrode into the body near to a nerve, and you inject the charge, and then you take that charge back. You don't have any net charge left because we regard any net charge being remaining there as being damaging to the tissue, and correctly so. But the fact that you have charge balance does not mean that you have balance in terms of chemical species, right? You're just looking, you see electrons coming back and forth. You don't know exactly what happened chemically. And what our research has been focused on for several years now is really mapping what chemical species are there during this kind of stimulation. So we discovered that really the key is oxygen. Oxygen is everywhere in the extracellular space. Obviously, it's vital for functioning of any tissue, but especially neural tissues, which are very metabolically hungry. You have a lot of oxygen in extracellular space, and oxygen is a strong electron acceptor. Oxygen wants to oxidize stuff, right? That's where the name comes from. So if we have an electrode polarized negatively, as we always do during the cathodic phase of stimulation, a lot of charge gets transferred to oxygen. And that oxygen can either turn into, it becomes reduced. So reduction of oxygen means that it's accepting electrons. It can either become water, or in some cases, it can accept just 2 electrons and split off as hydrogen peroxide. And hydrogen peroxide is a very potent and important reactive oxygen species. Both of these reactions, whether we're making water or we're making peroxide, both lead to a depletion of oxygen. They both consume oxygen. So what we established is that in the vicinity of neurostimulation electrodes, one is creating a hypoxic environment, an environment where oxygen is being removed. And in some cases, we're getting also the hydrogen peroxide. And the hydrogen peroxide has lots of interesting effects at different timescales. So, for example, we've done work about different types of ion channels, which are relevant in electrophysiology, that are sensitive to hydrogen peroxide. And for example, will stay open much longer in the presence of hydrogen peroxide and for example, cause cellular de-exciting the cells. So we started to, at first, this all started in the perspective of thinking about safety. Our protocols of biphasic charge injection, are they potentially leading to damage of tissues because of electrochemical reactions? And the answer is largely yes, that's an important mechanism. But this got us to the point that, we figured out there can be dangerous things happening. But what if we use very low direct currents to evoke these electrochemical reactions in a way that's orthogonal to neurostimulation? Again, we're using very, very low currents. So the amount of depolarization of cell membranes we get is very small, but we get meaningful changes in chemical changes. And indeed, we're looking at different molecules, but our real specialty is oxygen. So basically local deoxygenation or local creation of peroxide. This can have a strong neuromodulatory impact. And this is very exciting for us as scientists, that this is a completely new way of doing neuromodulation, and it's way too early to say if this is going to have super useful applications, but this has been unexplored.
I was actually about to ask if you see this as a method to investigate fundamental questions in life science, or if instead you can envision a technology in which we deliver some chemicals, some oxygen, in a targeted way to a tissue, so that we modify the activity of a specific tissue.
The answer is undoubtedly both. But after we've started to publish some of these first papers on this topic of modulating oxygen levels, modulating peroxide levels, I've gotten a lot of feedback from people who are on the fundamental side, who regard this as a very convenient experimental tool. They try to explore the impact of for example, hypoxia, right? So oxygen gradients, or Ross gradients, for experiments. People use all kinds of complicated ways of doing this. And we started really getting bombarded by people interested in it for experimental techniques that are unrelated to neuroscience. Mostly people studying metabolism, people studying redox biology, cancer biology, developmental biology, embryology, like all over the place, fields that were completely off my radar. And we started to get excited that, okay, well, people are like our research. That's great. We're very happy to provide some know-how and some electrodes. But one of my very entrepreneurial postdocs, Jirka Ehlich, he realized that there's a potential here, and together with him, we started a spin-out company that actually uses these electrochemical principles for in vitro biology. So these are essentially devices that are either at the level of cell culture plates or at the level of microscope slides, and they're able to modulate in a controlled, on-demand way, also in a multi-channel way. So if you have a cell plate, we can in different wells, we can select different conditions. We can have different levels of hypoxia in different wells. We can have different levels of ROS in different wells. Turns out to be super interesting experimental technique, because otherwise people either have to have an incubator that is hypoxic, and the whole incubator has one concentration, right? But now we can do it at the level of the cell plate, or some poor student is coming with a pipette and adding bolus additions of peroxide every couple of hours, which is also not only time consuming, it's also quite unnatural to have these spikes in peroxide concentration. So these continuous delivery systems of reactive oxygen species or hypoxia, turns out there's a demand there. Now we've embarked on this not neuroscience related startup company.
What's the name of the company?
The name of the company is Electrophorus. So it's from the Latin word like electricity carrier, right? So it's this word has some history in the old literature in the early days of studying electromagnetism, and it's also the name of a cool electric eel. Mm-hmm. Right? So we thought it's cool.
And this is a system that provides electrochemical oxygenation or deoxygenation effects in a multi-well system.
For example, yeah. So multi-well system is the most widely explored and the most highly demanded, I would say, from our partners. But you can also do it on a microscope slide. So for example, in a two-dimensional gradient form, right? Where you can have, for example, a lot of oxygen here, not a lot of oxygen here, and different concentrations in between. So combining that with microscopy method to see something in a spatially resolved way turns out to be also very interesting.
I've noticed this funny trend in your recent research using an unconventional animal model. So you use Locust for your experiments. What's up with that?
Yeah, so that's an interesting story. Started during COVID, actually, when we had very limited access to experimental animals, where few people in the group were actually doing experiments at home, basically taking home intents and recording equipment and digging up earthworms in the garden and just trying different things. So, and we started to realize step by step that hey, this is kind of cool. I mean, these invertebrate models, so insects and worms and leeches and things like this, they have the nervous system, right? And the nervous system is relatively simple compared to, of course, a mammal, but it's has the advantage of being very accessible and being also relatively well mapped and well understood. So these things are known in literature, what the different neurons do, for instance. So we started to use these kinds of models more and more to basically study if we're after these fundamental effects, like, for example, electrochemical effects on neural tissue or this high frequency stimulation effects on neural tissue. It turns out that a lot of these simple invertebrate models can give you a lot of answers very fast. And it's fast because in the European Union, most invertebrates do not count as experimental animals. So there's not the ethical issue, and I would argue that it's much more ethical to use these kinds of animals because you can prototype this on, for example, a locust, and then you can move on to a mouse, and you end up using much less mice because you've already perfected or somehow optimized your technology on the invertebrate. And also, of course, it's cheap. and it's very easy to get into the hands of students. So most of my students come from biomedical engineering background, and getting master's student or a bachelor student the right accreditation to do mouse experiments is just very inconvenient. But using, for example, locusts, which you mentioned, and locusts have become our favorite, right? Because they cost a few cents. You buy them at the pet store. You can get tens of them, and they are very, very good model for neuromuscular stimulation. They have a simple nervous system that innervates their famous jumping legs. So I should credit Bernhard Wolfram from Munich. He's the first one, I think, who really came up with this idea of using this model in the context of neural engineering. So we learned the model from him, and he does work with it, and now we really do a lot of work with it as well. And I mention this to maybe excite more people in the field to consider invertebrate models as a very convenient way to prototype ideas and prototype devices, especially because we all know in neural engineering, when you're making new devices, you make a lot of mistakes, you make a lot of errors, you make a lot of bad decisions in planning, and then you make something, you get to the mouse, and you realize you did something wrong, right? And then poor mouse, right? That's really ethically, I think, not so great. And if you make these kinds of troubleshooting phase of experiments on locusts, the tempo of advancement of the neural technology that you're interested in is much faster. And then by the time you get to the mouse, you're ready. You fixed your mistakes. You figured out exactly how the connectors should be. You are ready to get meaningful data from mice. So I just want to encourage people to think about things like leeches, cockroaches, and locusts as a way to obtain really meaningful experimental data.
That's very interesting, and I agree with you completely on the ethical side for the animal experimentation. But I also want to ask you, it's clearly important for this kind of applied medical research, the animal model, and it's getting increasingly complicated to have approved protocols, especially in some parts of the world, and I think Europe is one of these. I don't know in Czech Republic specifically. Do you think it's getting too complicated to access these animal experiments? And is this limiting the development of technologies?
I think broadly, my subjective opinion is that yes, it's getting unnecessarily complicated, and I understand and fully uh, agree with the ethical implications of having a respectful approach to animal experiments. We should not, just waste animal lives without meaning. We should think very carefully about it. But I do feel that most scientists generally have a fairly good ethical compass in this regard, and I'm not sure that the increasing limitations in animal experimentation are going to lead to anything good. The Czech Republic is a little bit better off than some of our neighbors like Austria and Germany, but we're also quite limited here. And this is also one of the reasons why I am all the more encouraged to use these invertebrate models, because this decreases the number of necessary experimental animals. Because I should say that invertebrates are all fun and good, especially if you're trying to answer like basic fundamental biophysics questions or just try out your device. They're fine. But when you want to explore real relevance to clinical translation, there has to be that step of the rodent or of the pig or the sheep. Some mammalian models have to be part of the story, and there's just simply no way around that if we want to create solutions that are meaningful for helping human flourishing.
Well, it was a pleasure talking to you today, Eric. Thanks a lot.
Thanks a lot, Matteo.
We like to conclude our episodes by asking our guests for a book that doesn't have to be necessarily related to your research, but a book that you really believe everyone should read. What would be your advice?
My book recommendation is Guns, Germs, and Steel by Jared Diamond, first published in 1997.
This book has affected many, and certainly made a big impact on my way of thinking. Guns, Germs, and Steel is a sweeping attempt to explain why human societies developed so differently across the globe. What I find most compelling is that Diamond was trained as a physiologist, and he applied the same mechanistic systems level of thinking to geography, ecology, and human history. The thesis of the book is a rejection of cultural and racial explanations for inequality between human populations. He traces global inequality to environmental and geographic factors, food production, and the diffusion of technology and ideas. This is a mechanistic explanation for many aspects of human flourishing, and indeed it sounds a lot like the way that physiologists try to explain how different organ or tissue systems work. For me, the book is not only fascinating in its conclusions, it's a powerful example of how stepping outside of one's disciplinary boundaries can unlock entirely new insights. As a scientist, I'm inspired by how Diamond used the tools of his field of training to illuminate big questions in other fields, and this shows just how transformative interdisciplinary thinking can be.